Hi everybody, welcome to section 4.7 on inverse trig functions. And our learning targets for this lesson is for you guys to be able to use correct inverse notation, not only in our representation as we write inverse functions, but also as we talk about them, how we say those. And we're going to be graphing the trig functions, these inverse trig functions, and finding some exact values. And also we're going to get into a little bit of composition of various trig functions as well. So a little bit of background, we covered inverse functions back in chapter 1. And if you recall, we could tell whether or not a function had an inverse that was a function by doing a couple of things. We had a couple of tests that we used, and one of those ways that we did that was to go ahead and check the vertical and horizontal line test. If our original function passed both of those tests, we said that the function was 1-to-1. And being 1-to-1 and passing both of those tests told us that the inverse function not only existed, but the inverse function was a function as well that would pass the vertical line test. So the functions we're studying right now, the trig functions, these are periodic functions and they do not pass the horizontal line test, but they're interesting enough to talk about and to study that if we go ahead and limit the domain, then we can study the part of the function that actually is or has an inverse that is a function. So a little bit of review. When we found inverse functions algebraically in the past, what we did was we exchanged the x and y variables and we solved for y. To find them graphically, all we did was we reflected them about the line y equals x. So here's our first trig function, the inverse sine function, also called the arc sine. You may see it represented either way. Most commonly you'll see the sine with the -1 exponent. That does not mean reciprocal. It does not mean sine to the -1 power. It is called the inverse sine. And the inverse sine function, this is our sine function right here from -pi/2 to pi/2. So if we limit our domain to those values, if we restrict the domain to just between -pi/2 and pi/2, then our sine function actually is a function. It passes both the vertical and horizontal line test. And so when we go ahead and do that, the domain of our sine function becomes the range of the inverse function. So notice how we have from -pi/2 to pi/2 on the y-axis, and then vice versa. The y-axis, or the range in the sine function, becomes the domain in the inverse sine function. So that's what those two functions look like graphically. Both are functions, and the second one is read the angle whose sine is. So whenever we're doing the inverse sine, we're looking for an angle as an output. So we're putting a ratio or a number in for x, and we're getting out an angle measure, usually in radians. And again, the range of the inverse sine, those are values in quadrants 1 and 4. We said from -pi/2 to pi/2 is our range, and so you can just think about that as being in quadrant 1 or quadrant 4. And it does include the values on the x-axis. The pi/2 and the -pi/2 are included in the range. So here's a couple of example problems on what we're going to do with this information on inverse functions. And we're going to find the exact values without a calculator. A lot of our reference triangle stuff, we're still working with that. Letter A says, find the angle whose sine is 1/2. Well, you know from the table that you memorized that the angle whose sine is 1/2 is 30 degrees, and we would represent that as pi/6 radians. The second one, the angle whose sine is pi/2. Well, the angle whose sine is pi/2, pi is 3.14, and if we divide 3.14 by 2, that's outside of our domain restriction. Our domain only goes from -1 to 1. This number is bigger than 1 if we divide it, so it doesn't exist. So be aware that you could get some things that do not exist. Letter C says, the angle whose sine is the sine of 5pi/6. Well, the sine of 5pi/6, that's a 30-degree reference angle, and the sine of 30 is 1/2, and the angle whose sine is 1/2, that, remember, our domain restriction, we're going to go from -1 to 1, and our range goes from -pi/2 to pi/2. So this is just going to give us pi/6 radians. It's just going to be the first quadrant reference angle. All right, down on the bottom, letter D. Evaluate the inverse sine with a calculator. Make sure you're in radian mode here. That's the most important thing that I need to make sure that you recognize. All of these, you need to have your calculator in radian mode. So if you're in radian mode, all you're going to do is pick the second of your sine function. It's a second function is the inverse sine, and just type in -0.81, and it'll pop out -0.944. Over on the other side, go ahead and take your calculator in radian mode and hit sine of 3.49 pi. That will give you a value, and then take the inverse sine, the angle whose sine is that value of your answer, and you should get -1.539. If you have any trouble punching this in, be sure to ask me in class and I'll show you how to do that. The inverse cosine function, or the arc cosine, we are going to limit our domain from 0 to pi radians. Okay, so on the x-axis we're only going from 0 to pi. This is now a function, okay, and it is 1 to 1. Our range is from -1 to 1, and that becomes our domain in our inverse function. So we're restricting our domain from 0 to pi, and our domain and range flip places between our original function and our inverse function. When we look at our cosine values, our inverse cosine values, okay, these values are in quadrant 1 and quadrant 2, because we go from 0 to pi are our outputs. From 0 to pi is quadrant 1 and quadrant 2. So on the cosine function, the inverse cosine, we will end up getting answers in quadrant 1 and quadrant 2. The inverse tangent function, we are going to go ahead and limit that domain from -pi/2 to pi/2. And that restriction does not include the endpoints. Okay, so you'll notice in the previous slides, it included the pi/2 and the -pi/2 for the sine function. It does not include it for the tangent function. So make sure you recognize that difference in the domain restriction between tangent and sine. And again, the domain becomes the range and the range becomes the domain. And for the tangent function, we're in quadrant 1 and quadrant 4 again, but the values on the x-axis are not included. So let's do some examples here. Find the exact values without a calculator. The angle whose cosine is -√2/2. Well, remember our cosine function goes from 0 to pi. So this is a 45-degree reference. So where between 0 and pi, quadrant 1 and quadrant 2, is the cosine negative? Well, they're all positive in quadrant 1. We know it's a quadrant 2 angle, and it's a 45-degree reference. So second quadrant 45-degree reference angle will give us 3 pi/4 radians. The tangent, where is the tangent? The angle whose tangent is the square root of 3. Well, that's definitely a 30-degree reference angle, which is pi/6. Oh, I think I have, no, I messed that up. Let me take that back for a second. That's a 60-degree reference. It is pi/3. And the last one, the cosine of -1.1, the angle whose cosine is that. And this is like an identity property here. Whenever you have the angle whose cosine is the cosine, these will always drop out and you'll just be left with the argument that you have in parentheses, which is -1.1. So that brings us to this slide. Okay, here is your identity property, just like we had in the last one. Actually, this one is very similar. Whenever you have the sine, cosine, or tangent on the outside and the inverse function on the inside, it will always be true that you will get the x value that's inside the argument there. On the ones that are on the outside, the inverse sine, inverse cosine, inverse tangent, you will only get the x value if it's in your restricted domain. Okay, and you'll see how that comes into play. Actually, we already had one example of that, but you'll see that it's always going to be just within your restricted domain. All right, composition of trig functions. Let's take a look at a couple of these. It says find the algebraic expression equivalent to the given expression. We want the sine of the angle whose cosine is x. So what you're going to do for these with the composition functions is you're going to draw your right triangle and you're going to label theta, just any angle theta, and we want to start out with the cosine of the angle being x. So the angle whose cosine is x. So if we look at this, the cosine is adjacent over hypotenuse. We're going to pick our hypotenuse to be 1 so that the cosine is x over 1. So we have this as being true. So now we want to find the sine of this angle. Well, the sine of theta would be the opposite over hypotenuse, so we need to find this other side a. We need an expression for a. Well, we can use the Pythagorean theorem using the two sides we already know. We can say 1 squared is equal to x squared plus a squared, and then solving for a squared, we end up with a is equal to 1 minus x squared, the square root. So now we have an expression for a. We can find the sine of theta, and the sine of theta will just be the length of a over 1. So the sine of theta is just 1 minus x squared, the square root. And that's your answer. Kind of an ugly answer, but that's what we get. So over here on the right-hand side, very similar. We want to find the cotangent of the angle whose sine is 2x. So again, set up your right triangle, pick an angle theta, and set up the angle whose sine is 2x. So opposite is 2x, hypotenuse is 1. Go ahead and solve for a. So you're going to have 1 squared equals 2x, the quantity squared, plus a squared. Solving for a, you end up with a being the square root of 1 minus 4x squared. Now write an expression for your cotangent function. Well, remember, cotangent is adjacent over opposite, so it's going to be a over 2x. And I hope I wrote this in here. There we go. A over 2x. And so side A is, and I have this as the reciprocal. I have this as the tangent function, so I need to just switch that for a second. So we need to flip this. It's 1 minus 4x squared, the square root, all over 2x. And I don't think it's going to let me do that. See if I can do this. There we go. Now I should be able to do it. Just need to unlock this. So bear with me for just a second here. And I'll go ahead and erase this and get the correct answer in there for you. Sorry about that. So I wrote the right thing, but then I switched it. So these should be reciprocals right here. And this will probably turn out to be a little bit bigger than the previous writing, but that's okay. So what we're going to get here, a is the square root of, oh, and then my pen's not going to work, really? The square root of 1 minus 4x squared all over 2x. So that is the correct cotangent for your answer. So here's a summary for you of the different properties for your inverse functions, your inverse trig functions, giving you what they look like, y equals the inverse sine of x or the arc sine, giving you the domain and the range of what the graph looks like. I just thought that'd be a neat thing to include as a reference for you. It was all kind of nice and condensed. And you can thank the Chaotic Gulf folks, Mr. Leckie and his cohort there from their website. That's where I pulled this from, so I wanted to give them a shout out and some kudos to them for having that all together. So that's it for this video. We'll see you next time, guys.